numbers and the golden ratio today. So in our past few classes, we've been looking at populations and different rules for how they grow. So we've looked at linear, exponential, and logistic growth are the three kinds of growth that we've seen so far. Can somebody remind me what linear growth is? What's the defining characteristic? Addition, yeah, always adding the same amount. Yeah, and how about exponential growth? Multiplication, great. And logistic growth, we didn't see a formula for, but what makes it different than the other two kinds of growth? Anybody remember? No. What makes logistic growth different than linear or exponential? What's its defining characteristic? We didn't talk about it for very long. Oh, this isn't on. Go back to a couple pages and we can see our logistic growth. This was our picture of logistic growth. That's the one that levels off. Yeah, that's a population that grows quickly at first and then slows down as it reaches a carrying capacity for the environment. All right, so not all populations grow according to one of those three rules. So we're going to look at a different growth rule today. And we're going to look at our first example of it having to do with bees. Okay, so female bees develop from a fertilized larva, while male bees develop from unfertilized larvae. So as a consequence, female bees have two parents, a male and a female bee. But a male bee only has one parent, just a female bee. Okay, so we are going to trace the family tree of a male bee back 3 generations. So keep in mind this is upside down. Usually when you draw a family tree as parents and then children underneath, we're going backwards, right? So this male here, its parent is a female bee. Okay? So we have a male, its parent is a female. This female has 2 parents, a male and a female. And then this male has 1 parent, just the female, and this female has 2 parents, a male and a female. So I want you to continue to trace back this family tree back 7 generations. And on the right, keep count of how many bees there are in each generation. So we have 1, and then 2, and then 3. Keep track of that as you go. And then once you fill out the chart, answer these questions at the bottom. You can discuss in your groups. All right, so let's discuss the results you've come up with. Okay, so I'm not going to build the whole tree. You guys can just tell me how many bees are in the next generation. 5, and then 8, 13, 21. Okay, good. So what pattern do you see in that list of numbers on the right? Think of that as a sequence. What pattern do you see, just in English? Yes, any number you get by adding the 2 numbers before it. Okay, so I asked you to write this in English because I thought it would be easier, but I saw many of you jumped right to the sequence notation that we've been using, which is really good because it means that that's starting to feel like a second nature way of explaining a pattern. So we'll write it both ways. So we would say P sub n, well, I'll write it in English first. Okay. So we would say each number is the sum of the 2 numbers before it. Good. All right, so I want to write that in the sequence notation that we've been working on for the past several classes. So P sub n, that could represent any population, any number in the list. The 2 numbers before it, I have to add the 2 numbers before it. So I'm going to have something plus something. So how do I indicate the number right before the nth number? P sub n minus 1. And then what number would come before that? P sub n minus 2. Great. That's the first example we've done where we've used a number other than just the one right before it. So it was really great that a lot of you came up with that notation. All right, so can you predict the number of bees 8, 9, and 10 generations back? All right, so how do you get the number of bees in the 8th generation? 13 and 21 gives you 34. So we've got 34, and then 55, and then 89. Great. All right, so now if you just count the number of male bees in each generation and see what kind of sequence we get here. So here we have, we'll put number of males in another column right here. I have 1 here. How many 1 generation back? 0. Okay, and then how many in 2 generations back? 1, and then 1 in the 3 generations back. How many were there 4 generations back? 2, and then 3, 5, 8. We get the same pattern. Okay, and what if we count number of females? How many females in this in the current generation? None. And then we have 1, 1, 2, 3, 5, 8, 13. Same pattern. All right, so this sequence of numbers is just an ordered list of numbers, 1, 1, 2, 3, 5, 8, 13. This is called the Fibonacci numbers. This list is called the Fibonacci numbers. And we use the same shorthand to discuss the Fibonacci numbers as we do any sequence of numbers, except this time we're going to call it F. Usually we use P for population, but we're going to use F for Fibonacci. So we say F sub n is going to be the name of the sequence, and the subscript tells you an address, right, where in the sequence each number lives. So F1 is 1, and F2 is 2, and F2 is 1, and F3 is 2, F4 is 3, etc. Okay, so if I want to find F8, right, the way I've written this out, what would F8 be? Okay, some people said 34 and some people said 21. What's the point of confusion here? 21, yeah. Why would we maybe think 34? That's F9, that's the next number in the list. And also in this example, the current generation, we started counting at 0, right? And when we talk about the Fibonacci numbers, we usually start counting at 1. So that's a little bit confusing. But if I look at just this list, the next number in the list would be 8 plus 13, which is 21, right? And then F9 would be 34, and F10 would be 55. So developing a recursive formula for the Fibonacci numbers, we already did that. Most of you did it in your groups before I even asked you to. So F sub n, the nth Fibonacci number, is equal to the Fibonacci number right before it, which is F sub n minus 1, plus the Fibonacci number before that, which is F sub n minus 2. And then we have to, in order to use a recursive formula, I have to give you 2 numbers to start with, right, to use this formula. So I give you F1 and F2, they're both 1, and we call them the seeds. There's also an explicit formula for the Fibonacci numbers, just like there's often a recursive and an explicit formula for the sequences we've been studying, but it's very unwieldy. It's got square roots in it and lots of fractions and powers, so we're not going to even bother with it. It is in your book if you're interested, though. All right, so let's just work with the recursive formula. And I'm telling you F39 and F40. I've given you the 39th and the 40th Fibonacci number. How could I find the 41st Fibonacci number? Add them together, yeah. F41, right? That's like my F sub n here. It's equal to F sub n minus 1, that's F40, plus F sub n minus 2. And 41 minus 2 would be 39. So I just add those two numbers together, and I have the 41st Fibonacci number. I'll pull up a calculator because those are big numbers. Four, 5, 9, 8, 6 plus 2, 3, 3. Okay, so I have 165,580,141. All right, so that one, we just applied the formula directly, right? I wanted the 41st, I added the 2 before it. What if I want to get the 38th Fibonacci number? Yes, great. Subtract, right? If I want to go backwards in the list, to go forwards you add, so to go backwards we should subtract. Yep, so F38, I'm going to subtract the 39th from the 40th. Okay, so I have 102.33 minus 39088. 39,088,169. So those are not that far into the list, 38, 39, 40, and those numbers are huge already. So this list grows really fast. So we call these numbers the Fibonacci numbers because they are named after a mathematician, among other things. He also was one of those guys who was also a philosopher and a merchant and all kinds of things, but he's a mathematician, and he lived around the year 1200. And his father directed a trading post in Africa, and he traveled there, and that's where he learned about Arabic numerals, which are the numerals that we use today, like 0 through 9, place value. And he helped introduce those Arabic numerals to Europe, which we cheer for because computations using Roman numerals is way harder than computation using Arabic numerals. But that was a really important contribution that he made. But the work that he's most known for is a book that he wrote called Liber Abaci. And in that book was a problem about rabbits. And this is the wording of the problem. A certain man put a pair of rabbits in a place surrounded on all sides by a wall. How many pairs of rabbits can be produced from that single pair in 1 year if we suppose that every month each pair has a new pair, right? Each pair produces a new pair, and they grow to maturity in 1 month, and then they start producing new pairs of bunnies. All right, so we're going to watch a quick video where we can see how this pattern produces the Fibonacci numbers. All right, let's see. I got to unmute this.